Hello, so this video will be a tutorial on how to deconvolute specs data. If you haven't watched my previous video already on what specs is and the logic behind it, please feel free to go watch that and hopefully you'll be able to follow along with this video quite easily. So just for the experimental data that I will be using today, this is the experimental setup that I used for this experiment. Basically, the most important thing here is that it's a non-aqueous system. We have a planar glassy carbon electrode, so it's a flat surface, no pores. Our electrolyte is 1 molar tetraethyl ammonium tetrafluoroborate, and it's dissolved in acetonitrile. And this is our potential window. And for the specs part of it, we did plus or minus 10 millivolt steps with 30-second rests in between each step. So this is the deconvolution part that we will be using today. So we have this equation here for the double layer component, this part for the diffusional, and this part for the residual. So as spoken about in the previous video, we change components, the resistance component, capacitive component, B, which helps the fitting take into account this entire equation here, and the residual component. And then with those altered, we use a sum of square residuals to reduce the difference between the experimental data and the synthesized data that we make from these equations. And hopefully you'll get something that looks like this, and this is what we will be doing today. Okay, so our group typically deals with our data with Excel. There is plenty other software packages out there and you can use whichever you like, but today we are just going to work with Excel. So just to start, if you watch my other video, you'll be familiar with this, but for this experiment, we asked the potential stat to record a data point every 0.1 of a second. Our steps are 0.01 volts. The rest period between each step is 30 seconds. And for this experiment, and I would advise it's a good idea to do so, we just have a 300-second rest period at the beginning before the start of the experiment. This is just to make sure that the electrode is nice and equilibrated and we have good specs results. And our potential window for this experiment is minus 0.3 to 0.8 volts. So this first sheet is just to show you how to split your data in case your potential stat likes to put the data for an entire spec experiment into a single column, which is a bit annoying. So we have our time, and as we said, we wanted it to record every 0.1 of a second. We have the current that it recorded, and it's in nanoamps versus the potential versus our silver iron electrode. So this nonsense over here is what Excel is using just to split it up. We like to deal with the specs. Each column is one single potential step. Basically, this column here is just a counter to help it, the Excel index it properly from this column here to be able to split it up. And then the same thing is going along here. So we asked the potential stat to record every 0.1 second, and we have a 30-second rest period. So that means for every potential step, we have 300 data points. And this for our beginning rest period is going to be 3000 because we have 300 seconds and it's recording every 0.1 of a second, so that equates to 3000. All it's doing is getting rid of the rest period, so counting 3001 points down, plus after this potential step, it moves to the next one. So this is just an example here of what it's doing. It's using the counter here and the counter here to be able to correctly index the single column here to split it up. So again, each column represents a single potential step. Okay, so this sheet is basically just copied and pasted what we did on the previous sheet here. If your potential stat puts the data out with the current per potential step in each column, you can just skip to this part. So we have our current in nanoamps here and our time here along with our potential along here. So each column now corresponds to one potential step. So Moving here onto our data, it's the exact same data again. We just omit this first potential step because most of the time it can be a little bit funny to get started with. So we usually just ignore the first one. So this sheet is mostly just normalizing all of the data. So in order to be able to obviously compare our data, we want it to be normalized. So if you had a material electrodes, you would divide it obviously by the amount of active material. For this electrode, we used a glassy carbon electrode, which is a flat planar surface, and it is a 3 millimeter diameter electrode. Therefore, it has a 0.0015 meter radius. And we know the area of the circle is pi r squared. So we just use that to calculate the active surface area of our electrode. So all that's doing here is then we divide the raw data in the exact same cell on, so it's raw data C15, so we come to raw data so C15, so in the exact same spot on that sheet. It's divided by this big number to make sure it is in amps and no longer nanoamps, and then we divide it by the area of our electrode. Okay, so this is probably the most important part, the actual deconvolution. We have our potential along the top. We have the potential difference between the previous potential, which is the potential step, so 0.01 volts, and then we get to the changeover point where we start going down in potential, it becomes negative 0.01 volts. So we have our parameters here, which we will be finding out from our deconvolution, and that is from the equation here. As we talked about before, we're finding the resistance term, the capacitance term, B for the diffusional part, and the residual current. So as we go along, these will gradually get filled out. We have our sum of square residuals. So we are using the sum of square residuals to reduce the difference between our created set of data and our experimental set of data. So this cell here is going over to this sheet here, and it is calculating the sum of square residuals between the normalized data, so C15, so it's using this cell here, and then as well analysis C15 and this cell here. So all it's doing is taking those two values and putting it into here to calculate the sum of square residual. And then this cell here is taking the entire column for this cell, so this whole part here, to get the total amount. And then basically when we use solver, it's going to change these parameters here to make this as small as possible. The smaller your sum of square residuals is, will mean that you have less of a difference between the created data, the theoretical data, and your experimental data, which is what we want, as low as possible. So all this nonsense going on here is this equation. So it looks a little crazy, but it's not too bad. So we have our residual, which is our constant here. We have to find b over t to the half. So we do t to the half with square root because it's the same thing. So this is the blue part. And then we have our double layer component, which is literally just this part here. It looks worse than what it is, but you should be able to see as well the coloring here to be able to match up what is going on. But all this is just on repeat this equation over and over again, as you can see. So it will be recreating the data based on what we put in here for our parameters. Okay, so let's go about making some guesses for the first column. The first part's the hardest part because you don't really know what you're dealing with, but as you move along, it's easier because there's only going to be a slight change between each potential step. So it becomes easier to deconvolute. So for the first one, the resistance, I'm just going to make a guess of 1 because it should hopefully be quite low for our system. Obviously, we want a relatively high capacitance, so it should be something like that. I'm going to guess 0.1 for the diffusional part, which obviously won't have as big a magnitude as the capacitance. And for the sum of square residuals, it's usually negative, so I'm going to go 0.01 to start off with. So we've times the sum of square residuals by 1,000 just to make it more significant for solver. So yes, this number is quite large, but it's not as large as it looks, if that makes sense. So this graph here is what I personally use to see how good my guess is. So the black dotted line is referring to, I'll show you here, this sheet on the normalized page. So it's plotting the exact same spot, so 0.295 volts. So it's plotting this column and it's versing this column here for the created data. So in black dots, it's this one, and in green, it is this one for what we've created. And we can see so far that they don't match very well. So I might change our capacitance up a little bit higher since the peak is a lot higher. So that made it a bit better. Let's try 40. I think that's good enough to start. Solver should be able to figure that out. This basically just is plotting as we go along just to see how things are. I just use that as a reference more towards the end to make sure Solver hasn't strayed too far and started funny answers. So for Excel, I'm going to go to Solver, load that up, make sure this is clicked onto a minimum. The objective I want to change is our sum of square residuals because we want to make that as small as possible as we discussed. And I want it to change these variables here to be able to make this as small as possible. Make sure this is unticked and this is set to minimum. And then I'll ask it to solve. So it has come back with a result. So I'm going to say yes to keep what's done. So that looks much better already. So we have the green line quite well overlaying the experimental data. The sum square residual has been reduced heavily and our parameters have changed a little bit. And you can see now that the created current, the modeled current, is now filled out as well. So that's our first guess. That's usually the hardest part. It takes a bit of getting used to come up with guesses. If you're really stuck, sometimes I just copy and paste the parameters from another experiment and see if that's a close enough fit. But usually Solver or whatever you may use is pretty good at figuring it out. So yeah, I personally keep continuing solving until I have an actual result. Once it comes to a solution, then I am happy. It's overlaying really nicely. And I'm happy to now move on to the next one. So I'm just going to drag this over here. I am now going to use Solver to change the next lot of parameters. I want to change this one and solve. Okay, so I'm quite happy with that. I have moved the graph over to be onto D. Same with the experimental data. It will now be sitting on D. So they overlay each other really nicely. So I am personally happy with that. To speed up this process, we do it in blocks of 10. So the sum of square residuals will do it in blocks of 10. So you just say, I would like to do that. I will just drag it along to here. I will use Solver to minimize this by changing all of these. So you'll basically do that in make it a bit faster. You can absolutely use programming to make this faster. We also have a macro inbuilt that can do it automatically as you go along. Okay, so hopefully when you're done, it will look something like this. So we obviously have the crossover point when we go back down to the other end of the potential window. So this is what our resistance plotted looks like, down to our capacitance, and then our diffusional part, which looks really nice, and our residual. The best one you want to keep an eye on is probably going to be the residual. You'll see some funny things otherwise, but this looks like good data to me. I'm very happy with it. For you at home doing this, I would be happy with any, I guess, software to deconvolute this for you, but I would always just watch for the crossover point, because you're going from a positive potential to a negative potential. You have a very big change. So for me personally, when I do it, once I get to the crossover point, I manually take care of the deconvolution part, the solver part, and then get it to start again once it's got some pretty good guesses going and I'm confident that it's stable and doesn't do anything funny. Yeah, just keep an eye on your data. If something goes incredibly high or incredibly low, especially as you're moving along, if these values aren't changing, so say this was the exact same as this one, then its solver has started to ignore one of the parameters and it's only just changing these parameters. So those are probably going to be the main issues to look out for. But as long as your data is really nicely overlaid, then you can be very confident, and as well with your sum square residuals is very small, then you can be very confident that you've done the fitting correctly and you've correctly deconvoluted your specs data. Okay, so the example I was using was for a planar electrode, but I am sure most of you will be using porous systems. There's not much of a difference. All we do is have two double layer components to make up for the difference between surface charging and porous double layer charging. Obviously, porous charging is going to be slower, so you need to take that into account by having another parameter. Literally, it looks the exact same. All you have now is two R and C components. So it just looks something like this. The starter's obviously already been done. It looks quite nice. And how you can tell the difference between which one is porous and which one is surface charging will be which one has the higher resistance, or which one has the slowest time constant. So this one here is just calculating the time constant. So this is for RC2 and RC1. So this one will obviously be for surface double layer charging, and this one, because it's a bit longer, is going to be representing porous charging. Sometimes they flip around because obviously they're the exact same thing. But just be conscious of that. And just to show you as well, sorry, so this is this equation going on here. All we've done is now got two of the double layer equations. So it looks a lot worse than what it is, but hopefully that will help you to deconvolute your specs data. Thanks for watching.